All right, so let's get into it. Today, when we talked about the formation of rock the other day, and we looked at sediment especially, we just started talking about the buildup of earth material due to glaciation or other types of movement and erosion forces, but we haven't talked anything about soil. And so we're really going to dig into this definition of soil because there's not really very many other factors, abiotic factors on planet Earth that contribute to productivity more than soil does. I have some interest in this just professionally, and I am not putting this on here. Don't take it as I'm trying to talk about my own work, but I'm just excited about this idea. When I did my graduate work on soil fertility, at the time it was just starting to go as an idea. People were really starting to study it with a new vigor, and now the number of scientists and research centers that are working in this, not because they saw my work and were excited about it, but just because of the relevance of it. All the topsoil on planet Earth will probably be gone in about 60 years. So it's in the same kind of global change sort of realm. Relevance of soil science is now on par to the amount of science that was happening in NASA in the year 1960. So there's a lot of revolution taking place. There's a lot of new science coming out. There are a lot of people who are focused on it because it's really critical. And we think maybe it's boring, but it's the relationship to productivity of biotic forces is really where the interesting part comes in. So only 2 learning objectives for today. We're going to talk about weathering and erosion and how those processes contribute to both the movement of elements throughout the soil. We'll talk a lot more about what those elements are and how crucial those elements are and the properties of those elements in our next unit. But we're just going to talk about the formation today, and then we're going to talk about the layers of soil and its formation, and there's a couple key things that we'll have to navigate as part of this work. So just 2 things to really accomplish for today. But in review, we've been talking a lot about rock, and these definitions are key to understand. So when we characterize rock, I know I've said this before, so it's redundant, but when we characterize rock, we're not talking about its properties in terms of what it's made out of, because all rocks could be made out of any sorts of things. Rocks are composed of minerals. So when I use the word minerals, we're talking about the actual elements and compounds and their crystalline structure that are actually forming these rocks. A lot of times, you'll see this come up on AP tests a lot, where they'll ask, well, what forms rocks? And a lot of times students think elements, but there are complex compounds that actually make crystals that are usually the ones that form rocks. And we have this amalgamation of aluminum combined with zinc and copper, and those things together will make one type of rock. So we know minerals are what actually make up rocks. So when I use the word rock, what you should understand in your mind is it's this aggregate of many different types of minerals, and that may include organic material, compounds that have carbon and probably oxygen and hydrogen as well, which is why some rocks are explosive and some rocks have combustive properties and can be used in all kinds of processes. But we're really thinking about an aggregate of minerals. And then the last thing is that some rocks are made of maybe just one mineral, but understanding this, and this is the second time that we've seen this as well, that shows one rock can become any type of other rock, and it depends on the agents of change that cause its formation. So you saw this on the quiz yesterday, but an agent of change, in this case when we're talking about rocks, there's really 3. We have erosion and weathering, which we'll talk a lot about today, which we saw an example with the glaciers, but heat and pressure, and by far, heat is the most transformative. So when you bring extreme temperatures that have the ability to take compounds that we usually find in a solid form out here in this area of Earth and heat it up until it becomes magma, that has the ability to change things the most. So we can go from an igneous rock, and you can actually convert it to another igneous rock if you melt it down. If we apply a little pressure and a little bit of heat, we can come metamorphic. That can go back this way. We can change either one of those to sedimentary rock. If we break it down into small shavings and convert that with pressure to sedimentary rock. So just knowing how to navigate this kind of flow chart as an example. Yeah.
Metamorphic rock is kind of like liquid.
So metamorphic rock, in our example here, we did only a little bit of heat. So if you remember in the lab, we did like half as much heat as we did when we were doing the igneous, and then we applied some pressure as well. And so usually in the spatial sense of where do we find this, the asthenosphere is where we usually have magma. So in order to get igneous rock, we have to put those materials all the way down into the asthenosphere, which is extremely hot, and turn it into liquid magma. And then when they cool, they become igneous. But if we're in that layer of the lithosphere, which is kind of close in proximity to the asthenosphere, it's not quite as hot. So we get some pseudo melting or some partial melting, and it's a little bit viscous. But we also get a lot of pressure, because if you think about that proximity, it's the lithosphere, the surface is here, and we're further down the lithosphere, so you have all of this layer of earth on top of it, part pressure and part heat. That metamorphic root word, you probably already know, means change, but it can also mean being transformed. So it's talking about it's moving from one type to another. If we keep applying more heat as opposed to pressure, it'll become magma, and then it'll become igneous rock. Does that help? Okay, excellent. So this I put on the slides and more as the reference for, so in your study, if you go back and you're looking at the slides as part of, I think this is actually a much better table to navigate. The flowchart diagram works well for some minds, but I think this sort of thing is a lot better. And it comes, it pairs really nicely with the textbook. So for example, we were talking about basalt and granite yesterday as two different forms of intrinsic versus, or extrusive versus intrusive rock, both forms of igneous rock. And so we have them under this category. The sedimentary rock, I had one student who made a really good observation yesterday. They were like, oh, don't press it down too much, it'll be really flat. Well, sedimentary rocks are usually really flat. So if we go to areas of Missouri, the key place where you can really see this is on 270 and 40, just down the road, where you have these layers of rock. It makes sense, right? Because the pressure is typically because of either ocean water or more rock on top of it. And so what is causing the pressure? It's gravity and weight. So those rocks usually are really flat. So sedimentary rocks, you have these layers. And the composition in terms of minerals, sometimes they're heterogeneous, meaning it's a full mixture, but you also see layers where you could have blue and then orange and then gray or brown, and that's because we have different minerals, and it would make sense that you'd have the deposition, especially from glaciation. As it shaves down certain rock, you get deposits of one type of mineral, and then you get a deposit of another type of mineral on top of it, and so you see these cool striation and layers. And then metamorphic, because of its density, it's used a lot in building materials. So some examples are slate, marble, and then coal is a really good example as well. So coal is deep. You know, we have to dig down and we're mining that coal, but we're not mining all the way to the asthenosphere. So the heat and pressure is from friction and from its position in the lithosphere, and then its depth. And all that pressure is what creates. We'll come back and talk about fossil fuels and coal a lot more later on in the class. All right, before we go to the next thing, what I want you to do is, like at your table group or a small group of three, I want you to think of one question and then ask your neighbor, and then we'll see if there are any questions to address before we move out of rocks into soil. Sound good? Just one question per person. All right, rock and roll. Go ahead. What questions do we have about the formation of rock? But ask your partner. There's got to be some questions, some unaddressed things. It doesn't have to be deep conceptual. It could just be something of interest. Silver, you know, rock.
same thing.
Any questions for the large group?
Is it head weight?
Nothing?
What's like the
Head weight?
like different types of igneous rock?
The two types of igneous rock, we've got intrusive, which are ones that cool under the ground. So they're not exposed to air or water. That's the big difference. Extrusive means they're on the outside. So those root words, those Greek root words, that intrusive or like exoskeleton or exterior or interior, those things go together. The key difference is not being exposed to air or water, and there are a lot of rocks that are being formed under the ocean. If you think about divergent plate boundaries moving apart and you're leaching out some of that magma, that's where a lot of new rock is being formed. It's all extrusive. It's exposed to water. It cools super fast. Yeah.
Is there anything different between extruded in the air versus extruded into the ocean?
Yeah, so good question. One cools a lot faster than the other. And it has to do with the specific heat. So some of that matters based on the temperature of the water. If it's deep ocean and it's really cold water, it'll cool faster. For most cases, we would think about things exposed to air cooling the quickest. Really? So because the air has the ability as a liquid gas, as a liquid properties, it's able to take and disperse that heat more quickly. So you've seen lava rocks that go in people's garden and it's got these pockets and it's super light, that pumice kind of rock. That's because those had been pockets of air. So that's volcanic rock that exposed to the air, and its density is the least dense, right? And if we think about that for the lab, that basalt that was formed, in that case, it's super dense, but it's exposed even though it's extrusive. Yeah?
Going back to basaltic or granite, this is one of the questions on the quiz.
Yeah. So according to our investigation yesterday, granite should be the one that's intrusive, and basalt is the one that is extrusive. There's some hints on that front packet. You won't find, I'm not going to ask you a lot about these specific types. It's too nuanced of geology to spend a lot of time on, but it's a really good exercise to interpret the phenomena of rock formation. So I wouldn't kill yourself to memorize all of these pieces. If you really know this line, moving forward in this class and being able to apply this to different contexts, that's going to be the key thing. This is just some supporting information. Yeah, go ahead.
It was like texture-wise, are sedimentary rocks more crumbly compared to like igneous rocks?
Yeah, and so that formation, the question is, are the structure of the rock, the igneous are the ones that are usually the hardest rock, and it's because of the way that they're formed, that magma, it's uniformly cooled at the same rate, and so it's extremely dense. The sedimentary rock, if I bring limestone in here, which is most of the surface rock in Missouri, I could break it apart super easy, right? Which type of rock do you think you would find the most fossils in, by the way? That's a good question. Yeah.
Sedimentary.
For sure, right? There could be fossils in the other layers, but you'd never know because you probably melted them.
It says phosphorus.
Oh, there you go. Yeah.
So, how exactly does pressure shape the rock? Because I know how the erosion shapes it with the glacier activity and how heat shapes it because of the whole flow chart. But how exactly does pressure itself make that change? Like, what are the steps with pressure doing?
Just gravity. So we're just thinking of weight and gravity. So the more stuff piled up, the more the pressure is because of the weight and gravity of a force of 4 newtons is just constantly acting, right? So we're just pushing the rock together.
Okay.
Yep, pretty simple. All right, excellent. Excellent. Let's keep going here. So what's interesting about this whole cycle, I just put this on here as a reminder of when we're talking about the movement and the cycling of rocks, we're looking at an extremely long period of time geologically. So Earth is about 4.5 billion years old as a planet, and this rock cycle has been happening since the planet took form, and humans have only been around and manipulating the geography of the land and moving rocks for at the longest about 10,000 years, but only in an extreme way in about the last 50 years. So our impact on the geological Earth processes has been extremely severe, but only within the last little bit here. It goes for a while. You can watch it later. But we're going to talk a little bit about now about soil formation. So the reason for mentioning all of this is we're next going to talk about the formation of soil. But when I bring up those facts around topsoil being damaged and soil being damaged, it's because we're disrupting this process that's happening that takes a really long time to occur. And our usage of the earth and earth material is mostly in the soil, and then a little bit more for geology, for things like fossil fuels and building materials, but this is the place where we're breaking it down the most. So a new word that you can think of as a synonym for rock is parent material. When I say the word parent material, or you see that word in literature, what they're talking about is the actual mineral and rock that makes up, or the bedrock that makes up the soil that is of concern or of study. And so when you think about that, think about rock. When you hear parent material, just think the word rock, but know we're talking about it in the context of soil. So erosion is a term that I know you all have impacted before, but let's just kind of step through it a little bit. Erosion is the physical removal of, here's a misspelling here, I meant to say rock fragment. And so we're breaking apart rock in a physical way. That could be people, it could be organisms, it could be weather. So weather, all forces of weather, extreme storms, wind, rain as part of weather, rivers, it could be glaciers, but it's actual physical things, and we're going to delineate that because we'll talk about chemical changes as well. But whenever we're talking about erosion, it's physical. So those two things go together. Make sure you have it straight in your mind. When we're talking about chemical, we have a new process. Let me go back here. Let me go back to this figure because I want to spend a little time. So at the beginning, before there were any biotic organisms on planet Earth, all you had was rock. And in places where new rock is being formed, you have igneous rock, and we're going to turn that probably on the surface level to sedimentary rock over time by applying forces of erosion. But this is completely intact. So immature soil resembles on the surface level parent material the most. And then over time, due to erosion, what are we doing with erosion? What is it again?
Physical removal of rock.
So if I have a big piece of rock and I'm going to force erosion, what does it look like after as opposed to what it looks like before? It's not as big. It's broken apart. So you can see this process taking place. It's really hard for organisms to grow into intact rock. So we actually need erosion to occur. And then over time, once biotic organisms start interacting in this area as well, we end up with certain layering, and the layering is dependent on both the speed of erosion and the actors of erosion. There's about 5 things that we'll consider that really contribute to the formation of soil. In this class and in your writing and your answers for this class, and hopefully any time going forward in your life, when you hear the word dirt, you're talking about just the abiotic chemical composition. You're basically trying to characterize just the minerals of the soil. Soil is a really complex thing, and it includes all the abiotic and all the other chemical attributes as well. And so in your writing, don't be surprised if I ding you. If you're talking about soil, but you're using the word dirt, those two things are not synonyms. So soil is formed through these types of forces. One is the topography. So in order for erosion to take place, erosion is going to occur if you think about water or glacier activity. It's going to act according to gravity. Water always flows downhill. So do glaciers. So the steepness of the grade of elevation is really going to be one of the key things that we'll study in terms of how quickly the soil is being formed. If it's steeper, there's going to be more forces of erosion taking place than if it's flatter. If it's flatter, you're going to probably have compaction, which is going to affect the soil in a different way. So soils are subject to erosion, and because of the other things that exist in the soil, that's really where we talk about topography. Climate, another big one. And what I want you to think about for climate, the reason that we do the earth science after I do the weather, in terms of our narrative about all of these interconnected natural systems that vary across space and time, is because climate is really a big driving force for how soil is formed. So in areas that are really productive biologically, we have organisms acting on the soil and drawing resources from the soil at increased rates. So places like the tropical rainforest, as an example, have really poor soil because the organisms are taking a lot of the nutrients out at a really fast rate. But those layers of soil are also being built up pretty quickly because of all the death and decay. And why is there so much difference of productivity at the equator or tropical rainforest than at 30 degrees north? Well, it's because of these climate forces and the convection cycle. So climate is a big factor as well. One thing that comes up, and we saw this when we talked about the glaciers, is that freezing and thawing. So water infiltrating into the soil and then freezing and expanding. That can break apart the rock, and then it melts and the water flows out. That process is a big contributor. So places that have this freezing and thawing versus places like Antarctica where it's permanently frozen, those areas have soil being developed at a much slower rate. So the latitude and longitude and the climatological forces have a big role to play. Organisms, which is fairly intuitive, you have all kind of things like small organisms, earthworms, small microbes and things like that that break apart the soil and draw upon the soil. They also decompose and contribute new material back to the soil. And these kind of things go together. So climate and organisms I usually think of as in one bucket because the number of organisms is driven by the climate and weather of a region. As we just looked at on the last slide, the amount of time that's occurred for all of these factors to act on the soil, well, that's a big play. If we have new rock and not much time has elapsed, then we probably don't have a lot of new soil being formed versus places where the soil has been intact for an extremely long period of time. The soil is being formed faster in those places if erosion and forces have already built up the soil. Last one here is the parent material. So dependent on what is the rock made out of. If it's extremely dense, it's inorganic and organic compounds, whatever those are, has a factor to play as well. So it's harder for erosion to take place in parent material that's a little more dense. That would make sense, right? Give a little time to write down what we have up here. All right, let's keep going. So now I want to do a little formative kind of exercise, and I'd like for everybody to attempt this based on, you have all the answers to address this in your notes and what you just talked about, but I want you to attempt actually doing this. So I heard a lot of feedback from students on the assessment that things are pretty tough in terms of timing. So I wanted to do a little coaching here before we get into these questions and attempt them. But whenever you see these words like describe and explain in the strategic and applied analysis, for an explanation, we're always talking about a process or interpreting some type of phenomena. So you're trying to explain why is this phenomena a true thing. So all I'm looking for in the answer is I need you to state whatever the scientific principle or law is at play, and then give a brief justification. So a 2-sentence answer is totally fine to address a question that says explain. To describe, we're usually asking you to use an observational clue. So here's some context about some type of thing. In this case, describe the development of soils and rock from parent material to mature soil. So I've already given you what the phenomena is of this process, and I just want you to describe the steps. So there's usually a step sort of thing. Again, 1 to 4 sentences, 4 is a lot, 1 or 2 is usually about right. Similarly, describe how the development, so we're talking about the process here, how those can occur simultaneously. So I want to give about 4 minutes, and that's the same amount of time I would give if this question appeared on a test, and you can scour your notes and try to give it a go. We'll take a couple minutes here. Try to pin the answer down in your notes as a practice exercise. My computer is frozen. I was going to use my musical timer, but it doesn't work today. Jet lag, you know. Right. You're all right. You all right? You can ignore the sheet. I'll talk about the sheet in a second. I was just passing it out while you're working. I'm really interested in what you can come up with for number 2, given your base knowledge from just this amount of talk. We'll go for about 1 more minute here, and then we'll talk about it briefly as a large group. All right, what did we come up with for number 1 here? What did we come up with for number 1? Who wants to give something out? Nick?
So as the immature soil goes to mature soil, there's less and less parent soil, or parent material.
So we have, this is good, a nice start here. So as we go from immature to mature, so we've already identified that there's a before, after, so we're definitely referencing a process. What's the second part you said?
There's less parent soil in the soil as it.
There's less parent material. So anybody want to offer any more or any amendments to that? Kate?
As parent material is eroded, there's more accumulation of organic material.
Okay, so this is a good layering on here. If we say there's less parent material, there's the same amount of actual stuff most likely, but there's less intact parent material. So it's broken down. So this is a good addition. Yeah.
At the same time, more organisms decompose and add nutrients.
So we have some more matter being added on from biological processes and biological cycling, which is kind of what we'll talk about here. A really good answer for this one. Who has anything else before I give a really good answer? A really good answer for this is on the previous slide. So how do we go from rock? Well, the formation of soil, you can say, well, factors like topography, climate, time, biological organisms break down parent material and through forces of erosion. So all of those factors cause erosion, which breaks down, and that pairs together. For a full credit answer on this, I would be looking for you to identify the types of things that actually cause that. So sure, I agree 100% with what you're saying about the less parent material is intact, but help me make the link, right? And it's these forces or these factors, right? So that's a good, yeah.
What about physical and chemical weathering?
Physical and chemical weathering. So if you just said chemical and physical weathering, that would be pretty good as well. A better version would just be naming what those processes would look like, because all of those act as that sort of thing. I'm interested in, I think we can do 2 and 3 as a group together, and we can build off of what was already said before. So we have certain organisms are dying and matter is being returned to the soil at the same time that erosion is taking place. So what do we have for the second answer? How do nutrient values change over time? Nutrient values. Yeah, Grant.
I said as time goes on, nutrient values will rise as the amount of organisms in the ecosystem continue to decompose into the soil, like dispensing the nutrients.
So on the decomposition side, the nutrient level is increasing, but what else is happening? Yeah.
Like over time, input from organic matter occur, and then that causes deep fertilization.
So we're increasing the fertility of the soil by adding. What else? Yeah.
Plants and other organisms that grow on the soil are taking out.
They're taking it out, right? They're taking it out. So this answer for number 2 is really dependent on how you frame number 3, or if you were given an example. If the decomposition is happening at a quicker rate than the erosion, then you're ending up with more nutrients in the soil. But if we're taking from the soil faster than we're either decaying material or returning it in the cycling, then your nutrient values are going down, right? And so I'd be looking for you to describe and maybe giving an example for a good full credit answer on that. Good. I've got a couple more things to talk about, and then we'll do a little more practice here in a second. Number 3 we did, we had kind of already addressed in our answer for number 1. You'll notice, I've tried to do this, by the way, and maybe you noticed it and maybe you didn't, but I've been trying to call out what is the really key terminology that you definitely need to know. And on this one, this is a must-know concept in this class. So we already know the processes that results in these different horizons, and we're going to take this from the bottom moving up. So we call each one of the layers of soil. If we are talking about parent material, that's just the rock. That's the underlying rock. But these layers, and it's super thin layers compared to the rest of the lithosphere, if we use that as a reference point. The deeper the soil, the healthier the soil. The more layers you have intact, the healthier the soil. But the layer that's the closest to the bedrock material, it's the least weathered, and it's because it's the least exposed. So this is farthest away from whatever factors of erosion. It's the farthest from water, it's the farthest from roots, it's the farthest from all of those 5 things that we talked about. This is going to have the least impact, so it's going to have really large particle sizes. Really large particle sizes, because they haven't been broken down very much. We call that the C horizon. Above that is this B horizon. So now the particles are getting a little bit smaller than they are in the C horizon, and we also have this key thing happening. So if you look above that, we have the A horizon, which is kind of the topsoil, and the O horizon, which is not really, we consider it in the soil, but it's just decaying material. So it's dead plants, it's dead insects, it's organic material. So the O is for organic, and then the rest of it is kind of alphabetical. But the A layer is this topsoil, and the B layer is this subsoil. And so what happens is, as rain and weather processes and as roots use and move material, you get this accumulation of metals and nutrients that are water soluble. So if we have rain and you have something that can be dissolved in water here, it's going to move, and it can only move in one direction due to gravity. Water is always going to flow down. So it's moving all of those water-soluble materials from A to B. And then we have this weird thing in the middle called the E horizon, which is the zone of leaching. That's where the leaching is referring to that process of the movement of that metal material. So anything that's water-soluble in the topsoil over time is moving towards the subsoil where it's accumulated. So this area of the soil has some relative toxicity to it, even though the layers above it are really healthy. So the farther away that B layer can be from the A layer, the healthier your soil complex is. We'll talk, and we're going to deal with this in a lab setting in a little bit, or in our lab tomorrow. So O is organic, A is topsoil, E is this zone of leaching in between A and B. B is the subsoil, and C, you'll usually hear a synonym like bedrock, and it resembles the parent rock. And then underneath this, we would have full-on parent material. Sound good? Yes, Kate. Oh, yeah. So the longer this is, or the more space this is, the healthier the soil is going to be. So because we have this accumulation of metals and sometimes nutrients, but too many nutrients, too many cations, which we'll talk about tomorrow, that's the better it is. And I'm sure you've heard of that before. Well, topsoil, if you have a lot of topsoil, oh, well, your soil is really healthy. Yeah, of course, it makes sense. That's a true statement. Yeah, feeling good? The horizons is a must-know sort of thing, yeah.
So if the B is really close to the A, it means a lot more stuff is getting leached from the A?
If the B is closer to the A, it just means that there's less space. So as roots move through the topsoil and get to this area, they're getting to this area of kind of toxic-y soil a little bit quicker. So you want a nice thick layer of organic material and a thick layer of topsoil. And some soil doesn't have a zone of leaching. It depends on what the parent material is.
So the smaller E is and the larger A or they are, the healthier.
You got it. And E and B can be really big layers as long as A and O are really big layers too. So we're going to do some soil columns tomorrow. We'll go out in the field and actually collect soil as part of an exercise for this sort of thing. But if we go to places that have really good soil, we can get a soil core like this. Our stuff out here, because of curated, manicured land and heavily landscaped and moved material, it's like that much soil. So it's not that healthy. All right, I have one more thing I want to mention. I'm going to skip this exercise, which I think is a good formative exercise, but it'll be on there. And I just want to turn to this document really quick so that we can come in with our feet on the ground for tomorrow. So there's two more formative things that you can do as practice on this end of this slide, and I'll update it at the end of the period with the video, and you can go on there and see a couple examples. But turn your attention really quick to this document. So this is called a soil triangle. This is called a soil triangle. I'll let you keep yours, and I'll hold up a different example. And essentially what this is a graph with 3 different variables on it. And so what we're trying to understand with this is what type of soil are we dealing with? And so the first thing that I want to notate on this, you can put it in your notes or on this document directly, is that sand is the largest particle size, silt is a medium particle size, and clay is extremely small and dense particle size. Sand is big, silt is medium, clay is super small. Which one do you think is going to be the deepest, according to what we've just learned? Keep in mind, whoever's closest to the forces of the erosion is getting broken down the most.
Sand's going to be on the bottom, clay's going to be on top.
Sand on the bottom, silt on top of that, clay at the top. So in order to navigate this, if you do a measurement and you come up with something like, we'll do our first example, 40% sand, you start on the sand axis and you're going to go all the way around this in a clockwise fashion. So I go to 40 on this scale, and you're always going from the lower left to the upper right. So 40 of sand, and then I go and try to see where that line intersects the clay, which is here, or excuse me, the silt, which if I go in this way and work my way around it, and it should give you, as you go around the dial, where those 3 points intersect is the characterization of the soil. So we're going to do a little bit more with this exercise tomorrow. You don't have to worry about finishing this worksheet. This is a totally formative thing, but I wanted to give it to you and just talk about the properties of this, and we'll work more on navigating it tomorrow. Yeah.
Can you explain this one more time?
Yeah. Which part of it?
How to read it.
We'll do more with the reading of it tomorrow. The main thing, I just wanted to get it out to you and know that sand is the lowest, silt is in the middle, and clay. If you've got that in your mind, we'll work with the soil triangle tomorrow. Can Justin or Evan, will you just stop the recording back there? Otherwise, you guys are good to go. Have a great day.